greatest burden of morbidity and mortality associated with prostate cancer are due to its complex, multifaceted, heterogeneous nature, in conjunction with its slow progression and tendency to remain dormant, which make it highly capable of undergoing metastatic invasion to distal organs. Whilst all of the hallmarks of cancer contribute to the burden of prostate cancer, its metastatic spread significantly reduces survival rates of patients. Thus, our current proposal aims to target and reduce metastasis by intercepting the metastatic pathway and reducing angiogenesis. For prostate cancer cells to become malignant, the cells must undergo epithelial to mesenchymal transition and escape their primary location in the prostate by traversing into the blood or lymphatic circulation. The basement membrane, which separates the extracellular matrix from the epithelial cells, is comprised of type 4 collagen, creating a scaffold of heparin sulfate, laminin, and other proteins. Tumor cell invasion occurs by degradation of collagen 4 via tumor cell-induced recruitment and activation of type 4 collagenase. Upon invasion, tumor cells also initiate angiogenesis of nearby vessels to provide a new blood supply to nourish its progression. Tumor angiogenesis occurs due to signaling from cells degraded in metastatic invasion or from the tumor cells directly to promote the release of vascular endothelial growth factor (VEGF) to bind to the VEGF receptor on nearby blood vessels. Activation of these tyrosine receptor kinases initiates several downstream pathways which regulate transcription and initiate angiogenesis. Prostate cancer usually occurs due to genetic damage to cells, which initiates oncogene activation and inflammation of the damaged site. Tumor cell-mediated release of inflammatory cytokine stem cell factor binds to the c-KIT receptor on mast cell surfaces, recruiting them to the site. Mast cells undergo degranulation in response to the acidic environment surrounding the tumor cell, releasing stored secretory granules that contain bioactive mediators including histamine, heparin, and proteases including chymase and tryptase.
Tryptase, a hidden protease which accounts for approximately half of the product within mast cell granules, is activated upon dimerization with a highly negative glycine proteoglycan, heparin. This binding event allows autocatalytic intermolecular cleavage of tryptase, followed by precursor dipeptide removal to initiate the active tryptase tetramer formation. Tryptase activates the protease-activated 2 receptor PROR2 on the epithelial surface of prostate cells via catalytic proteolysis of the receptor. This initiates a signaling cascade through activation of the MAP kinase pathway to initiate increased mRNA transcription of metalloproteinases, pro-MMP3 and pro-MMP9. Plasminogen-activated conversion to plasmid allows activation of pro-MMP3 to MMP3, which can then catalyze the activation of active MMP9. Active MMP9 can then activate collagenase activity to facilitate the breakdown of the extracellular matrix for migration and angiogenic vascular neogenesis. In addition, MMP9 acts to increase inflammatory cytokine release, thus recruiting more mast cells and promoting a positive feedback loop. The tryptase tetramer is made up of 4 non-covalently linked subunits with centrally facing active sites that form a central binding pool. This acts as a selectivity filter for substrate binding. Positively charged amino acid residues on the active site surface are present to facilitate ionic binding to negative substrates, such as heparin. In addition, the 6 loops on each active site provide added steric hindrance. While scatterin inhibitors exist for mast cells and heparin activation of histamine and other mast cell mediators have beneficial factors such as anti-tumorigenic activity. Thus, by inhibiting the active heparin binding site within tryptase, this seeks to reduce pro-tumor activity whilst retaining the anti-tumor activity of mast cells. The tetrameric tryptase active sites contain 2 clinically relevant binding pockets, S1 within tryptase monomers and S4, a pocket which sits between 2 adjacent monomers. Binding to S1 is found to be facilitated by drug moieties which bind negatively charged arginine residues via hydrogen ion bonding to competitively inhibit the S1 pocket. Binding selectivity for β-tryptase will be facilitated in our approach by exploiting binding properties of the S4 pocket. The addition of a rigid phenylethinyl aryl group on inhibitors induces rotation of an S4 pocket residue, tyrosine 95, to reveal a buried hydrophobic pocket known as S4+. We seek to design a drug with hydrophobic carbon-hydrogen side chains to bind this pocket and produce a selective tryptase competitive inhibitor. Our drug will be administered by a once-a-day tablet with a standard release of the tryptase inhibitor, which will selectively target beta-tryptase from mast cells. Liang and his colleagues in 2012 demonstrated that these compounds are already available. Your money will allow for further studies into quantitative structure-activity relationship models and structure-based drug design to elucidate the specific drug properties that can bring this vision to life.
It will help us eliminate the difficulties in achieving the drug specificity to the selective, narrow binding pocket, refine our drug's effectiveness to the many well-known pathways of prostate cancer, as well as determine the drug's optimal bioavailability in reaching the cancer cells. Additionally, if needed, it will assist in evaluating the administration bioavailability via subcutaneous injections. The applications of this particular inhibitor are wide due to the influence of tryptase throughout inflammatory processes. Hence, this drug could be furthermore used to treat conditions including asthma and arthritis.